Okay.
That's how the 4 ions.
Oh, yeah. So there's 3 sodium ions, right? And 1 phosphate. Does that make sense, Alex? Cool. Any other questions about this before we move on? It's a great question. Cool, cool, cool. All right. So now we're going to get into ionic equations. Okay, so these are pretty much exclusively going to be double D reactions, right? So let's do a simple one to start. So we have sodium chloride being reacted with silver nitrate, and we're forming sodium nitrate and silver chloride, which is a solid. Okay. Now, again, you don't need to know why silver chloride is a solid, but as a general rule, silver tends to be really insoluble, so it often will make things, make products that are not soluble, aka solids, right? Why is silver soluble over here?
It's with nitrate.
Exactly, right? It's hooked up with a nitrate, and we know that anything that's hooked up with a nitrate will always be soluble, right? Does that make sense, guys?
Mm-hmm.
Cool. So that's a kind of question that I could ask you on an exam or a quiz, right? So silver nitrate is soluble, but silver chloride isn't. Why, right? You don't need to know why silver chloride is a solid, but you do need to know why silver nitrate isn't a solid. Does that make sense? Cool. So when we're writing out these chemical equations, basically what's happening in this reaction is we're forming a solid, right? What did we say the fancy $25 name for a solid formed in a chemical reaction is? It starts with a P.
Electrolyte.
P. Precipitate?
Oh, that's way
Yeah.
back.
Yeah. So precipitate, right, is the fancy way of saying that we formed a solid in a chemical reaction, right? So one of the things that we want to do a lot of the times with these double D reactions is there's a lot going on in this reaction, but not all of this information is really relevant to the solid that we made, right? So what do I mean by that? I got sodium chloride and silver nitrate, right? And they're coming together to form this solid and these other guys, right? But when we do the dissociation of everything that's soluble here, right, we'll find that there are some ions that are represented on both sides of the equation, and we can cancel them out, okay? So let me show you what I mean by that. So if we break up everybody, meaning we're dissociating all of the ions that are aqueous, right? We can only dissociate things that are aqueous, not solids, not gases, not liquids, okay? So dissociate AQ, not solids, liquids, or gases, okay? So what are the ions that we form when we dissociate sodium chloride? Oh, sorry, Alex, I think you might have missed earlier when we were talking about solubility rules, but nitrates are always soluble, and group 1 metal ions are always soluble, right? And you can go back to the beginning of the video later on and check that out. So, what do we form when we dissociate this guy? What ions? You guys scared of me today? So we got sodium, right?
Chlorine is -1.
Mm-hmm. We have chloride, right? Now what about when we dissociate this guy?
Silver plus.
Mm-hmm. We got silver plus and
Does it stay together anyway? NO3?
it does, right? So just a reminder, when we break up ionic solids, the polyatomic ions do not break up, right? They stay polyatomic ions. So, is everybody comfortable with how we got to there? Cool. And then on the product side, I'm going to go down a line, sorry, because I don't have room. What will this guy dissociate into?
An A plus.
Mm-hmm. So we've got another sodium, right?
And then NO3 minus.
Mm-hmm. And another nitrate. Yeah, exactly, Kata. Is everybody comfortable with that? Now, if you're wondering why I wrote them like this, it's because we're basically going to do a little bit of subtraction from the reactants to the products. But I have to write my solid that I formed, right? Which again, when we dissociate, only things that dissociate are aqueous, not solids, not liquids, and not gases. So we have silver chloride solid, right? Doesn't break down into ions. Does that make sense, guys? Y'all with me?
Mm-hmm.
Cool. This is called the total ionic equation. Okay? Total ionic equation, aka TIE, because I'm too lazy to write that. Now, what we want to do once we have the total ionic equation, or the TIE, is get rid of any ions that are on both sides of the reaction arrow. Any ions that are on both sides of the reaction arrow means that they're not involved in the chemical reaction, aka they are spectators. They're just along for the ride. Not chemically reacting. Does that make sense?
It's chloride and silver, which is what is left over on the other side.
Mm-hmm. So the next step that we want to do once we have the total ionic equation is we want to cancel out the spectators, right? So anything that's on the reactant side and the product side, we're going to cancel out, right? So sodium cancels with sodium, and nitrate cancels with nitrate, right? And what that gives us is the net ionic equation, aka the NIE, right? Which is going to be Ag plus Cl minus goes to silver chloride solid, right? So whatever's left over after we cancel out the spectators is what we put in the net ionic equation. Everybody all right with me on this one? Cool. Questions? So why would it be important to know what the net ionic equation is? So just for starters, we're not looking at limiting reagents here. So we're not actually talking about quantities of reactants yet, Alex, but we'll get there. Yeah. You're so ready for the stoichiometry in it. I love it.
Good question.
Yeah.
What if it doesn't always equal what's left over as for the product?
Mhm.
Does that make sense?
Yes. So if that was the case, then you hadn't balanced properly, right?
Cool.
So in this case up here, it was pretty simple because they were all 1 to 1 to 1, right?
Yeah.
But in a more complicated case, you can imagine that there's a lot of ions floating around, right? And it can get kind of messy. So if you find that you no longer have a balanced equation when you come down to your net ionic equation, then you didn't balance it in the first place, okay?
Gotcha.
Yeah, great question. So when we're looking at the net ionic equation, hopefully you guys will agree with me that this is a lot simpler and easier to understand what's going on than this thing, right? This one kind of just gets straight to the point, right? This is what's happening in the chemical reaction. Everybody else was just kind of hanging out, right? But if we know that all of these species are aqueous, right, then what that means is they're ions in solution, right? So when you're looking at this reaction, what starts out as two clear liquids, right, aka homogeneous solutions, now becomes a clear liquid and a solid, right? So I don't know if you guys remember from a million years ago when we did experiment 4, I believe it was, where we had the, we formed silver iodide. It was kind of a yellowish, powdery looking substance. But when you form a solid in aqueous reaction, it doesn't always look like a solid the way that we would think a solid looks, right? I don't know about you guys, but when I think of a solid, I think of something that's kind of coalesced into like a crystal, right? Something that has like definite solid looking form. But that's not always the way that solids look when they're formed in a chemical reaction, right? A lot of the times they just look milky. And that's because those solids are usually suspended in the solution. So, but it doesn't mean that you didn't form a solid, it just means that you might have to get the solid to coagulate to make it look like a solid. Does that make sense? Kind of, sort of. Cool. Any questions about that? How we doing with this stuff, guys? I know we're going into a little bit of overtime, but I kind of want to do another example, a little more complicated example of total and net ionic equation, okay? Obviously, if you have to tune out, it'll be on Canvas later on, so don't stress. Okay, so let's do beep boop beep bop. I know I use this example a lot, but it's one of the more complicated to balance when you're dealing with ionic solids. So that's why I use it a lot. But potassium or sodium phosphate are really common ones you'll see me use. Okay. So if I have these two guys reacting, right, what products will I form?
Potassium chloride and copper copper phosphate?
Yeah, exactly.
Okay.
Right? So we have, potassium chloride, right? So I think I mentioned this before, you guys, but I like to literally just write the ions up top here because it makes it a lot easier for me to see how they're going to change partners. Oops, minus. Does that make sense? So if I have potassium ion has a +1 charge and the chloride ion has a -1 charge, then I just need one of each to make a neutral ionic compound. You guys with me there? Cool. Soluble or insoluble? Why?
Group 1 metal.
Group 1 metal. Group 1 metals are soluble, right? So this guy is aqueous. Okay? And then copper has a +2 and phosphate has a -3. So how many coppers do I need? I need 3 coppers for every how many phosphates?
2.
2. Does that make sense, guys? Everybody all right with that? Cool. And phosphates aren't always insoluble, but it's pretty common that they form solids. So again, this is something I would tell you. You don't need to know that, okay? What's up, Jessica?
How did you get... First of all, how do you always know that? But also, how... Oh, because the... No. I got it.
Cool.
Got it.
So how do I know that this is a solid? Because I've done a lot of chemical reactions. That's it. I mean, there are more detailed rules that literally say this is insoluble with that, and you can look that up, right? So you guys ever look at the wikis for a lot of these chemicals that we're working with? No? Well, the wikis tell you about their solubility. So if you were to look at the solubility of potassium chloride, you can probably get 10 to 15 grams, I'm guessing, to dissolve in a liter of water, maybe more. This guy would be like milligrams maybe per liter, right? So that's one of the ways that we look at solubility, right? How much of this thing will dissolve in water. There's always going to be like a little bit, right? But if it's only a little tiny bit, we basically call it insoluble or a solid. Does that make sense?
Yeah.
Cool.
Well, I'm sorry. Like I'm just like getting a little overwhelmed. So
Yeah.
why did copper switch partners?
That's what a double D is.
Okay, so
We're always swinging our partners do-si-do, right? So we got a cation and an anion hooked up over here. We got a cation and an anion hooked up over here. And the double D basically says, what if these guys switch places, right? So now I have a cation hooked up with this anion, right?
Which makes it solid.
Yeah, if we form a solid. So we don't always form a solid, okay? The ones that we've been looking at so far have formed solids, but they don't have to. Yeah.
Okay.
Yeah.
Thanks.
We'll look at a quick example of that after we're done with this. Okay?
Okay, cool.
Okay, so what's my next step?
I forgot we were doing double Ds.
Let's break them apart.
Uh-uh.
No? You don't want to see each one thing in...
I want to get there. Before I can go to the tie, there's something really important that I have to do. Yeah, I got to balance it. Right? I got to balance it. So I have 3 potassiums over here and 1 over here. I got 1 copper here and I got 3 here, right? So things are not balanced. So before you go to the tie, you have to make sure your equation is balanced. So, which one you want to balance first? Which one?
Calcium? I mean...
Copper?
Potassium, sorry.
Potassium?
Yeah.
So, here or here?
Yeah.
Here?
Yeah.
How many?
3.
3, yeah. 3.
All right, we're going to try it this way.
Am I?
Is it wrong?
No, let's do it. So, all right, we balanced potassium now. What about phosphate?
I don't like it. No, erase it.
So we put a 3 here, right? But we have 2 phosphates on this side and only 1 phosphate up here, right? So we need to balance the phosphates first. You guys with me on that?
Okay.
Yeah.
So, put a 2 in front of it?
So we need a 2 out here, right?
Okay.
Now remember, this 2 multiplies by this 3, right? So now how many potassiums do we have? 6. Does that make sense, guys? Everybody with me? Now we have 3 coppers over here. So how many do we need up here? 3, right? Am I balanced?
Oh, yes, you are.
I did it, right? So I know it's kind of counterintuitive, but a lot of the times I start with the more complicated looking thing because that's usually where the balancing gets tricky, right? Starting with the easier looking thing usually ends up being harder. So does that make sense, guys? I know it's kind of weird and backwards, but that's how I think about it, okay? All right, so now we have a balanced chemical equation. Now we can do our tie, right? So we have to break up our aqueous reactants, right? So what are we going to form on the reactant side?
So we got some potassium.
Separation, multiple subscript from the 2. I think I understand what you're saying. So the 6 multiplies by the 1s here. Is that what you mean, Alex? No. You're talking about up here? Sorry, my thing died. You talking about that? No, it's okay. So we have 2 times 3 is 6 ions of potassium, right? And 2 times phosphate means 2 phosphate ions. You guys picking up what I'm laying down there?
Yeah.
Cool. I think it'll make more sense, Alex, once we break it up into the tie, right? It's kind of hard to see here, but once we break it down into the tie, then you'll see all of the ions. It doesn't multiply. The subscript on phosphate here is 1. Does that make sense, Alex? We didn't write it.
Put them in parentheses.
Yeah, so we didn't write parentheses around it, but if we had, there would be like a little 1 out there, right? Yeah. And if that's easier for you guys to remember, if you like putting the parentheses around the polyatomic ions, please be my guest. Do that. That's fine. Does that make sense?
So when we break them up,
Yes.
it's 2 potassium and 2 phosphate?
Ooh. 2 times 3.
No, I know, but when we're about to break them up,
Yeah.
so it's 2 and 2. Oh, so it's... Oh, well, I wrote 2K3. But... Oh, we just... Okay.
Yeah.
Gotcha.
Right? And this kind of goes back to the dissociation reactions, right? So remember when we were talking about the dissociation of sodium phosphate? We said we started out with 1 molecule, right? But we ended up with 4 ions, right? So in this case, just because we started out with 2 molecules, right? We're going to end up with more ions down here. Does that make sense, guys? And then, how many phosphates?
2 phosphate.
2 phosphates. Right? What else?
2 copper.
2 copper?
3.
3 copper, right? 3 copper 2s.
3 copper 2.
And what else?
6 chloride.
6 chloride. Is everybody comfortable with how we got that?
Yes.
There's a tiny reaction arrow over there. Sorry, you guys, I'm going off the page. All right, and then on my product side, what do I got?
6 potassium.
Mm-hmm.
6 chloride.
Mm-hmm.
And then 3 copper and 2 phosphate.
Do we break up solids?
No. Trick question.
So we never break up solids, liquids, or gases, right? Only things that are aqueous. Right? So we keep copper phosphate as a solid. Any questions about how we got what we got there?
Let's cancel some stuff.
That's my favorite part. Slashing them. Get out of here. So what can we cancel? What are our spectators here?
Potassium
Mhm.
and chloride.
I agree. So our spectators are potassium and chloride, right? So when I cancel those out, what do I get for my NIE, my net ionic equation?
Two phosphate
Mm-hmm.
plus 3 coppers.
Equals that solid?
Yep. Sorry, you guys. We got a little ugly there at the end, but does that make sense? Kind of, sort
I
of.
have a question.
Yes.
So for like on a quiz or exam, when we have to work out this problem,
Yes.
we're gonna need to write out the full equation like this, not just like the answer of the solid.
Correct.
You need to be able to solve the
Yes.
full equation with both the reactants and the
Yes.
solid.
So the way that you guys would see this on an exam or a quiz is you would be asked to give me the tie and the NIE, right? So you would have to have the whole thing. They'd have to be balanced, right? And you'd have to have phases on everything, right?
Will we also have to know the spectator?
Yes. Mm-hmm. Yeah, absolutely.
Okay, thank you.
Yeah. So a lot of the times I'll ask you parts of those questions, not like the whole thing. So it's difficult for me to ask you guys for a whole tie and NIE because there's a lot of opportunities for you guys to lose points on those. So a lot of the times what I'll do is I'll say, here's a chemical reaction, right? Here's a double D. I gave you the reaction. I gave you the balanced reaction. What are the spectators in this, right? So you would need to be able to identify the spectating ions, right? In order to do that, you kind of need to know how to do the tie and the NIE, right? So a lot of the times the questions that I'll be asking you are, you still need to know how to do the whole process, right? But you're maybe not having to give me all of the steps. Does that make sense? But I guess that's kind of moot. That's kind of moot at this point because you guys are showing your work for everything now, right? So you would show me the tie and the NIE for this too. Yeah. So yeah, you'd be showing me all this. So.
I don't know why I keep getting confused. And when we write, I understand how to write the tie for the reactant, but I don't understand the product part.
Oh, so we no longer have these guys, right? Because we canceled them out. You with me? So the only thing that's left on the product side is this guy. I know it's kind of annoying because I have this written over 2 lines, and it's way easier if you can write it all out on 1 line, then you can see. But I just don't have the space for it. Sorry.
Okay.
Okay, so real quick, I want to give you guys an example of a reaction with no PPT, right? Or nothing formed, essentially. So let's say we had sodium chloride reacted with potassium nitrate, right? What would our products be in this case?
Sodium nitrate.
I'd have sodium nitrate and what else?
Potassium chloride.
Potassium chloride. Soluble, insoluble.
Soluble.
Why?
Group 1 metal.
Group 1 metal and
Nitrite.
a nitrate, right? Does that make sense, guys? So this guy is definitely aqueous, right? What about this guy?
Also soluble.
Also soluble because
Group 1 metal.
group 1 metal, exactly. Does that make sense, guys? So if we do a tie for this, what are we going to get?
You say everything gonna cancel out.
Yeah, exactly. Everything is spectators. Do you guys see that? So if everything is a spectator, then there's no reaction. Right? Nothing happened. So in the previous problem, right, we said we'd start out with a couple of clear liquids and we'd end up with a kind of cloudy solid, right? But here we'd have clear liquid, clear liquid, clear liquid, and clear liquid, right? We didn't form anything. Does that make sense, guys? This is kind of one of the points that's annoying for not being in lab, because I think understanding these reactions is a lot easier when you can actually see the reactions. So that's why I'm trying to give you guys a visual understanding as well. So, does that make sense, guys? So in the case that everything is aqueous, nothing is basically happening here, right?
Can you tell me what PPT stands for again?
Precipitate. We're just too lazy to write it. And by we, I mean me. Any other questions about these guys? Cool. So the next class we're going to get into some solution stoichiometry, and we'll start in on acids and bases, okay? Cool. And by the way, again, I apologize that the homework is not up yet for chapter 11. I'll have that up, chapter 9.